Moving forward a little bit in history here, we're going to go to the times of antiquity, the height of the Greeks and the Romans, and even a little beyond that. Let's talk about things in the sky, first of all. The stars. Night after night, the stars don't seem to move relative to each other. The Big Dipper looks like the Big Dipper, and Orion's Belt looks like Orion's Belt. Ancient people thought they had a handle on that. They pictured the sky as a giant celestial sphere curving around the Earth, and they felt confident they could explain things when certain constellations were going to rise and so forth. Fine. The sun and the moon. Now, of course, they thought the sun was literally rising in the east and going through the sky and setting in the west. We know that's from Earth turning, but even though they were wrong, they could easily predict when the sun was going to rise, where it was going to rise on the horizon, when it was going to set, and so forth. Same thing with the moon. Very easy. They felt good about all those things, but there was one thing that really threw them off. The planets. Now keep in mind, they could only see 5 planets with their eyes. Mercury, Venus, Mars, Jupiter, Saturn. Those were the 5 that they could see. And this really threw them off. Matter of fact, the name for planets, planetas, means wanderers, because the planets seem to have a mind of their own. They just seem to be, they could clearly tell they were different than stars, for example. One small difference, not only difference in motion, but even the brightness. We know that's because at different times, planets are a different distance from the Earth and from the sun. But they might interpret that to mean Mars was getting angry because it's getting brighter or something like that. But the really big thing that threw them off more than anything else is something called retrograde motion. Retro, back, right? If something's retro, it's going back. Retrograde is when the planets appear to drift backwards in the sky. Just watch. Let's watch of what it would look like if you watched Mars night after night. What would happen every once in a while? Let's watch. So here comes Mars through Leo. It's cruising along night after night through December, January. All of a sudden you get to February and it turns around and it goes backwards. And then you get to April and it turns around and goes forward again. It's pretty tough to explain, isn't it? Most people watching this probably are like, hey, I can't explain that either. So we can't really blame ancient people for being sort of freaked out by that zigzag that planets make every once in a while. But they came up with some clever ideas on how to explain it. Now, some of the key characters here, let's talk about Aristotle for a minute. Aristotle. One of the key figures in human history, really. But every time I mention him in my class, it's something he's done wrong. He was a big supporter of the geocentric theory, Earth at the center. He also really liked the idea that everything in the heavens had to be sort of perfect. Perfect circles, perfectly smooth objects with perfectly circular orbits and so forth. Aristotle is the Einstein of his day. You know, he comes from the school of Socrates and Plato and him. I mean, he's sort of royalty as far as the great thinker of his age. He's like Einstein. If Einstein tells you something, you're probably just going to go with it, and that's what people did. So he was a very powerful voice, and unfortunately, he was dead wrong on this whole topic. Versus, let's say, this guy, Aristarchus. It's funny, we've all heard of Aristotle. Aristarchus, what did he do? Oh, not much. He just got it right. He was the first person we know of who actually suggested that perhaps the planets go around the sun. He brought up the heliocentric theory, but unfortunately, at the time, he couldn't prove it whatsoever. As a matter of fact, he probably had his idea shot down pretty quickly. First, for some, kind of basic reasons, they would probably say to him things like, hey, if Earth was flying around the sun, we would feel that, we would know that. Of course, they didn't understand that Earth is moving in the vacuum of space at a almost constant speed. So we're not going to feel that. They made arguments about the wind, that the wind would blow the birds right out of the air and so forth. But again, not realizing in the vacuum of space, that's not going to happen. There were even some, other reasons that they had. But the only good reason, the only good scientific reason, I should say, that they had against him, and this is a good one. They said, we're not detecting a parallax shift. If the Earth was going around the sun, the stars should seem to shift position. It's like if you look at your thumb with your right eye and then switch to your left eye. When you switch, your thumb is going to, shift. That's a parallax shift. And your right eye and looking with your left eye is the equivalent of Earth looking at a star in June and then going around the sun and looking at that same star in December. It's like looking at right eye, left eye. The stars should shift. If we truly are, let's watch this little thing here if this will work. Not sure if this will work. Oh, there it goes. So here's the Earth going around, and we're looking at that red dot there. And as the Earth goes around the sun, look at this. Against the background of stars, if you look at the top there, that object would be shifting back and forth, a parallax shift. That is a good, logical, scientific reason that Aristarchus lost the debate. They weren't detecting a parallax shift. But what this also illustrates, let's watch it again real quickly. It's important. Watch what happens here. Here the red dot is fairly close to us. And you notice it's a very large shift. Now watch again. Now we move the red dot farther away. Oh, now the shift is smaller. If you try the thing with your thumb, line your thumb up with something in the room, look at it with your right eye and then with your left eye. But now move your thumb even farther away and do the same thing, and you will see a smaller parallax shift. The farther away something is, the less that it shifts. Guess what we know about stars? Yeah, they're pretty darn far away. When the closest star other than our sun is over 24 trillion miles away, that's a very small parallax shift. So there was no way in ancient times that they could possibly measure it, and poor Aristarchus had his idea shot down. Now, a little bit later in time, more towards the height of the Roman Empire, we had another really brilliant person named Ptolemy. Ptolemy lived in Alexandria, Egypt. I think he was of Greek origin. And he wrote what some sort of called the Bible of astronomy at the time, the Almagest. That's not even his name for it. He actually named it in Latin Syntaxis. But later it was named the Almagest, which means the Great Book. It's one of the most influential books in human history because it literally was the book of astronomy for centuries. For hundreds of years, people turned to this book. I'm sure there were a lot of good things in it. But unfortunately, on the real big topic, he got it wrong. He, unfortunately, was still under the shadow of Aristotle and tried to keep a geocentric, Earth-centered universe or solar system. And he tried to keep Aristotle's perfect circles. Now, the way he did it, I give him some credit, was kind of clever. If you look at this down at the bottom, to explain why Mars would go into retrograde every once in a while, he would just have Mars cruising along and then suddenly do like a loop-de-loop. Now, what happens during that loop-de-loop is that during part of that circle it's making, it would appear to go backwards from our perspective and then go forward again. I think that's very clever. Yes, it's kind of silly having the planets all doing their little loop-de-loops as they're going around the sun. Of course, he had no explanation why they would do that. But he called these loop-de-loops epicycles, and that was his way of explaining retrograde motion. Unfortunately, over time, this just didn't hold up. So over the centuries, it kept getting more off. They wouldn't make the predictions like it did because it's wrong. It's just wrong. And so they started adding loop-de-loops within loop-de-loops to try to make it work. But it was a big house of cards, if you will, that was all ready to collapse. We'll talk about how that collapse occurred next time. But first, here's a little bit trying to explain how his epicycle would explain retrograde motion. Let's watch it one more time. Now watch, as Mars is going forward, now when it does its loop-de-loop, it appears to go backwards for a bit and then goes forward again. I think that's pretty clever. All right, speaking of clever, I think this is the greatest experiment of ancient times. I didn't know exactly where to throw it in the notes, so we're going to throw it in right here. Let's watch and listen. I'm hoping the sound picks this up all right because this video explains this so succinctly and with such cool little graphics. I'm just going to play it and just let it roll here because it's really cool. Let me get it going here. I rarely do this, but I can't do it any better than this. This is just a perfect 2-minute explanation. I'm going to turn the mic around, maybe, and just let it go. If I can find the play button. There we go.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth, 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in the ground. That man was Eratosthenes, a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. The sun was directly overhead. He wondered if this were also true in Alexandria, so on June 21st he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities, and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees, so 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
That to me is just so amazing. I think the greatest experiment of ancient times. Put a stick in the ground and measured the circumference of the entire Earth just based on the shadow of a stick. Unbelievable. So really cool stuff there. Here it is, just a picture showing we're in Syene on the summer solstice. They knew that the sun had to be directly overhead. The sunlight could get to the bottom of the town well. So he knew where the sun was directly overhead, and then he found out that it wasn't directly overhead on the same day at the same time where he was at. And then he realized that little slice of the Earth represented just part of the entire sort of pie piece. And you can do a simple ratio, and to get within 1% error. Incredible. And I just want to point out that obviously they knew at the time that the Earth was round. It wasn't like Columbus or Magellan or anybody that proved that. They knew in ancient times. For example, the shadow of the Earth during a lunar eclipse is clearly round. That's just one way that they knew the Earth was round. The way ships approach from a distance, you know that the Earth is round. So they had plenty of indications that it was round. And it's kind of hard to believe that people in this day and age, there are some that still, for some reason, think that the Earth is flat, which I don't quite understand. Speaking of brilliant, one last thing, the antiquity mechanism. This is one of the greatest archaeological discoveries of all time, and it just totally changed our thinking on ancient times. This was discovered, this is cool, this was on a shipwreck. It was discovered, the shipwreck was discovered about the year 1900, but it was actually from a ship that wrecked 2,000 years before. Now, they weren't sure. They found this piece of brass here, and they had no idea what it was. It sat on a shelf for decades until technology got better, and they were able to peer inside, and they started realizing, hey, there's some interesting things going on there. And they find these gears. And as time goes on, as our technology got better, we started realizing how these gears worked. And now our minds are just blown. This thing, some people call it the first computer. It was amazing. It could actually predict the motion of the planets. It could predict eclipses. It actually included things like the fact that the moon's orbit is slightly elliptical. It was absolutely so advanced. They've recreated it now And it's incredible. It just totally changed our thinking. We think it's the most advanced instrument on the earth of that time and held that title for hundreds and hundreds of years. Antiquity mechanism. Make sure you check that out sometime.